Bien, bonjour à toutes et à tous. Bienvenue donc, à cette journée de la Revue d'histoire des mathématiques organisée dans le cadre du séminaire d'histoire des maths de l'IHT. Merci d'être assez nombreux. Toujours plus nombreux. Et donc, pour commencer cette journée, nous avons le plaisir d'accueillir Veronica Gavagna, qui nous vient de l'Université de Florence, en Italie, qui est membre du comité de rédaction de la Revue d'histoire des mathématiques et qui va nous parler des travaux sur les polyhedra réguliers à la connaissance et en particulier du cas de Francesco Maurolico.
Oui. Merci. It's better this one. Yeah, okay, perfect. Thank you to the organizer for this invitation. I'm sorry, I'm going to talk in bad English, but if you have, if you have questions in French, I'm glad to answer to you. And my talk will be divided in two parts. In the first part, I will introduce the figure of Francesco Maurolico, and in particular his attitude, his approach toward the problem of the restoration of the Euclidean tradition, the Euclidean elements in particular. And in the second case, in the second part, I focus my attention on the case of his study of regular polyhedra, and in particular to the problem of filling space with regular polyhedra. And what about his life? He's one of the most important Italian mathematicians of the Renaissance, and he was born in Messina in 1494. He became a priest. His first publication is in 1528, is a book about grammar. Latin grammar is not very important for this reason, but it's important because in the preface he explains his ambitious program of publication of classical Greek mathematics. And in the same year, on the behalf of the Senate of Messina, he started teaching Euclid and the sphere of Sacrobosco. In 1543, he published his second book, is a book on cosmography, and he has the structure of dialogue. Some years later, 10 years later, he finally got some funds to publish his work, but this editorial project did not work very well, and in fact, he published only one volume in 1558, is a volume on spherics, Theodosius, Menelaus, and so on. And 10 years later, he began teaching at the Jesuit college. And in this case, he started a new editorial program about which I'll talk some minutes later. In 1574, Christophorus Clavius, one of the most important Jesuit in mathematics, went to Messina to help Maurolico in publishing his writings. And for this contribution, the year later, appeared the Opuscula Mathematica that contains Maurolico's edition of book 13, 14, and 15 of Euclid's Elements devoted to Platonic solids, and the Arithmeticorum Libri Duo. But as far as we know, we don't know the contribution of Maurolico to this publication, because in that period he was ill and he died the year before. And so, as you see, Maurolico left to us only a few printed books, because the great amount of his heritage is in manuscript. We have more or less 5,000 pages of manuscript and printed edition, that's a small part of this. And so the Maurolico project that began in Pisa many years ago had the aim to publish Maurolico's work. As we have seen, in 1528, Maurolico began lecturing on spherics and Euclid's element. And his first approach to the element was very unsatisfactory from his point of view, because the available edition of the elements That means the edition of Zambertti, published some years later, some years before, in 1505, and the Campanus edition, published by Rattold, were, from his point of view, very unsatisfactory. Why? And we have here an overview on some passages of Maurolico's paper, where he explained why he is so critical toward these editions. He says that something of Campanus edition are to be accepted, something has to be rejected, refused, and that he says that Zambertti has no sense of mathematics, so his translation is very bad. And he translated more or less literally without understanding the mathematics behind the text. Another passage, he mentions the edition of Jacobus Faber Stapulensis that simply put together Zambertti's edition and Campanus' edition, but without refunding the text. And the last passage, he underlines again that the available editions are very bad, very unsatisfactory, and this is the reason why he began his Euclidean project, we can say it. And he explained in a dedicatory letter to Barresi the aim of his project. The aim is to make Euclid easier and more correct from a mathematical point of view. So we here see his first approach that is not a philological approach, but a mathematical one. He's not interested in restoring Euclid, but in restoring the mathematical sense of his elements. And his project, we can summarize his project in this work, Emaculare, Faciliorem, Reddere. And what does it mean? Emaculare means clean and correct the number of mistakes, not mistakes of concepts, of the printed edition. Eduobus unum opus cooptare, or to merge the available different tradition, each time choosing the most streamlined logical architecture, the most convincing proof, the most suitable terminology. It's not excluded in particular cases that the existing proofs would be replaced by new Maurolican proofs. So he's a mathematician that is working, not a philologist. And finally, Reddere Euclidem Faciliorem. That means simplify and shorten, where possible, the Euclidean proof. Simplify and shorten in arithmetical way, the great part of the cases. This is his program, of course. And of this project, we have some manuscript extant. That's the redaction of book 2, 5, 7, 8, 9, and 10. And they are in a manuscript form. They were written between 1532 and 1541. But of course, as you have seen, we have the missing draft. We have no news about the missing draft of books 1 to 4, 6, 11, and 12. Even in the various version of his Index Lucubrationum, sort of list of his works, he mentioned always a complete edition. So we don't know, as far as this moment, if he had actually wrote the missing draft or simply he didn't do it. Anyway, even if his Euclid was not published, his Euclid was his reference text in all his work. And in fact, we can see in the Arithmeticorum Libri Duo, he mentions propositions of Euclid that are all in his draft and not in published edition. And actually, in the second part of his life, he has a new program on Euclid, a program that was born by his relationship with the Jesuit. And actually, in the late 40s, the Jesuit Gerolamo Domenech, with the help of Ignatius of Loyola, founded in Messina the Collegium Primum ac Prototypum, with the purpose of creating a model of Jesuit university open to external students, not only for Jesuit students, and he had to be the University of Messina. And for this reason, the Jesuit of Messina thought to invite the most important scholars of that town to collaborate to this program of education. And Maurolico was very old at the time. Anyway, he began his second ambitious editorial plan for arranging all the sciences in an encyclopedia structured in compendia. And such compendia were to be used not only, of course, in the Collegium of Messina, but in all the colleges of the Jesuit society all over the world. And for what concern the Euclid, Euclid's element, he wrote a compendium divided into 3 parts, more or less. He wrote in 1567 the compendium of book 1 to 10. He reworked one of his booklets written in 1563, and this began the compendium of book 11 and 12. And then he took his lesson written in 1532 on books 13, 14, and 15, and this began the last book of his new compendium. And this last part that means book 13, 14, and 15 were published in 1575 in Venice. When, of course, we have just a question about the anecdotal point of view. Can we really consider this merge, this very composite text, a real unique edition? Of course, some objection arises. For example, we have different dates of redaction. The dedicatory letter of book 13, 14, and 15 is dated 1532. The booklet was on a solid figure were written in 1563, the new compendium in 1567, and we have many other editions that he added later. And we have different styles of writing. For example, in some books we have more or less no demonstration, but only phrases like patet, it's clear, and something like that. In other versions we have long proof, and so it's very heterogeneous also from this point of view. And we have different sources used by Maurolico. For example, in the first 10 books, they are self-contained in the sense that all the references are internal. For what concerns books 11 and 12, it follows the numbering of Campano's edition. And for what concerns books 13, 14, and 15, he follows Campano's, except for book 10, where he follows Gamberti. So it's a mess, exactly. But we have notes written by Maurolico, a note on a manuscript where he says, here we have a short version of book 11 and 12. And so we have the compendium of all Euclidean books. The first 10 books are collected in another book, together with arithmetical issues and beautiful demonstrations. Book 13, 14, and 15, devoted to regular polyhedra and enriched with proposition, are conserved in a book devoted to Pietro, namely Barresi. So, Maurolico's instruction is to put together this text, but it's so amazing that actually only the last 3 books were actually published in 1575, and the other books, the other redactions of the books, still remained unpublished. And so we now focus our attention on these last 3 books, devoted to regular polyhedra, of course, and we can see in this table is the sense of Maurolico reworking. We have here the number of propositions in Maurolico's edition, in Campano's edition, and in Zamberti's edition, and we see that numbers are quite different. To be honest, also Campano's tradition and Zamberti's one is quite different, but Maurolico adds a number of propositions. Not only adds, he says in his preface, in book 13, we added 1 proposition, which is the 6th one. The addition allowed to insert also proposition 14 and 19. So he reworked also the architecture of these 3 books. Then, it follows, we moved 2 propositions, the 7 and 12, from book 14 to book 13, because proposition 7 is useful to prove proposition 8 and proposition 12. Furthermore, proposition 12 makes easier the proof of proposition 4. And he says, in book 14, I added 25 propositions starting from the 4th. It was a necessary addition because without those propositions, the theory of solid figures was incomplete. Actually, in Hypsicles' work, the 14 books was attributed to Hypsicles, dodecahedra and icosahedra were compared with respect to surfaces and volumes, but the comparison of the other 3 regular polyhedra was quite ignored. Why? So his purpose is to complete the theory of a regular polyhedra that was incomplete, even in the Campano's edition and both the Zamberti's one. And so another time we see Maurolico's approach is a mathematician at work, is not interested at all in the restoration of the text of Euclid, of Hypsicles, and so on. Is interested in make a complete mathematical theory of this object. And we find here some results that he presents in the 14 books about the relation, numerical relation between surfaces and volumes of regular polyhedra inscribed in the same sphere. For example, he states that the surfaces of a tetrahedron is to the surfaces of an octahedron as 2:3, or that surfaces of the cube is to the surfaces of the octahedron as 2 to radix of 3, and the surfaces of cube is to surfaces of octahedron, and so on. And he established a sequence of the values of the volumes of the solid inscribed in the same sphere, and he says that the volume of the dodecahedron is greater than the volume of the icosahedron, the volume of the cube, and so on. And the analogous relation between the surfaces of the same solid. And so he put in correspondence volume, surfaces, making a sort of arithmetical calculus. He make a lot of calculation of these values. Does not work. Oh, stop. Okay. This is on the contrary, his version of book 15. The first 5 propositions are present in the Greek Latin tradition. As we remember, the Greek Latin tradition contains only 5 propositions. And they speak about the problem of inscription of one regular solid into another. And they are construction problems. The first one is how to inscribe a tetrahedron in a cube. The second, how to inscribe, you see the figure on the right, how to inscribe an octahedron in a tetrahedron. Third, how to inscribe an octahedron in a cube, and it's easy, it's enough to use proposition 1 and 2. 4 propositions inscribe a cube in an octahedron, and the last one, a dodecahedron in an icosahedron. At this point, we have only the Greek Latin tradition, but in the Campano's redaction, we have more propositions, and Maurolico follows Campano, adding proposition 6, how to inscribe a tetrahedron in an octahedron, using proposition 1 and 4. An icosahedron in a dodecahedron is the converse of the 5, a cube in a dodecahedron, an octahedron in a dodecahedron, and so on. And so how to inscribe one solid, solid figure into another. And yes, in the Greek Latin tradition, we have also some addition. The first one is very trivial. Is book 15 explains how to calculate the number of edges E and the number of solid angles V in the 5 regular solids respectively. The formulas are obviously this one. The number of edges is equal to the number of sides of the face times the number of the face divided by 2, and the number of the angles, the vertices, is equal to the number of the vertices of one face times the number of faces divided by the number of edges concurring the same vertex. Very trivial formula, of course. The second observation, the second remarks on the book 15 is more interesting. It's not present in Maurolico's edition of this book, but it's a suggestion for a new book he was going to write. And this suggestion is how to determine the angle of inclination between faces meeting in an edge of any one of the solid. So how to measure the dihedral angle. And this is the methods suggested. The dihedral angle of the tetrahedron is measured by the plane angle BEC. And in fact, you have to draw the perpendicular BE from the vertex B to the midpoint E of the edge AD, to draw the perpendicular CE from the vertex C to the midpoint E of the same edge AD. And of course, we have 3 equilateral triangles, ADB, ADC, and ABC. And it's easy to state that the square of BE is to the square of BC as 4 is to 3. And then that the square of BC is less than the sum of the square of BE and the square of CE. And so it's easy to conclude that the angle BEEC is acute. And this is the last remark of book 15 in the Greek Latin tradition. As I've already said, this suggestion is not present in Maurolico's edition, in Maurolico's version of book 15, but this argument, this topic of mutual inscription of solid gives him some suggestion about how it's possible to fill space using this circumscription of one solid into another, and taking the heritage left by a booklet written by Johannes Regiomontanus. This booklet has this title, On the 5 like-sided bodies that are usually called regular, and which of them fill their natural space, and which do not, in contradiction to the commentator on Aristotle, Averroes. Maurolico was largely inspired by Regiomontano's program in his work. We can consider him as the heir of Regiomontano's. In all Maurolico's life, he tried to conclude this editorial program. It was not so lucky, but he tried to do it. And this problem, the problem of the booklet of Regiomontano, was very interesting. And actually, the booklet of Regiomontano was not extant. He only mentioned in his program, but there were no manuscript, no printed books, and nothing about this. And the aim of Regiomontano's work was to confute a mathematical claim of Averroes, that was, as you know, a commentator of Aristotle. And Aristotle asserted that of the 5 regular polyhedra, not only the cube, trivially, but also the tetrahedron filled space. But Aristotle gave no evidence of this. Among the commentators on Aristotle discussing the number of tetrahedra that can fill space about a point, Simplicius asserted that the number of such tetrahedra is 12. But he gave no reason of this. Averroes proved, in some way, that 12 regular tetrahedra met in a point and filled space there. How did he prove? He introduced a sort of theory, a very strange theory of measure of the trihedral angle. And he says that the measure of trihedral angle is simply the sum of the face angles that form it, that concur in the vertex. Thus, the measure of the vertex angle of regular tetrahedron is 180 degrees. And since 8 cubes fill the space about a vertex, a necessary and sufficient condition for space filling by tetrahedra is that the sum of the trihedral angles meeting at the point be equal to the product 2160. In fact, the solid angle of the cube is 270. Times 8 is 2160, but 2160 is also equal to 12 times 180. And so it's the same, filling the space with 8 cubes from this point of view, and 12 regular tetrahedra. This is very amazing proof, of course. And actually, Maurolico, in the preface of his booklet devoted to this problem, says, our booklet on the plane and special figures with field space, this is the preface, although it's certain that Johannes Regiomontanus has written in great detail on this, this work has never been published as far as I know. We show now in this booklet that of the regular bodies of the cube itself and pyramids together with octahedra filled space, whereby it will be clear that Averroes erred in a childish way. Of course, the theory of the measure of trihedral angle that I've already mentioned before is absolutely erroneous, of course. And so, in this book, that whose title reminds to the title of Regiomontano, De quinque solidis que vulgo regularia dicuntur, que videlice theorum locum impleant, et que non contra commentatorem Aristotelis Averroes, it's quite the same. And it's usually known as libellus de impletione loci, book on the filling the space. He wrote this book in 1528, 1529, and he tried to restore the Regiomontano's lost booklet. This is his aim. And in this booklet, he approaches the problem of filled space with the regular polyhedra, proving that cubes and other patterns fill the space. Maurolico's objection to the theory we have already mentioned, or bet the result that 12 tetrahedra fill the space around the point. Maurolico's objection is obvious. If 12 regular tetrahedra fill space about a point, then they would together form a convex polyhedron with 12 equilateral triangular faces, which would be, of course, the 6 regular solid, and we know that we are only 5. And so this is not possible. This is also the objection moved by Thomas Bradbury. And Maurolico says that we have, while in the plane, we have only one way to tiling the plane, that's disposing the figure around the point. In the space, we have two approaches. And we have, we can fill in space about a vertex, verticaliter, or filling space around an edge. And this is angulariter. Of course, the filling space around an edge implies the filling space about a vertex, but the converse is not necessarily true, of course. And so, this is the first problem. We have two ways of filling space. And the other problem is, what does it mean, fill the space? Are we sure that when we find a pattern that fills space, actually this pattern fills space totally and not only locally? That's this pattern, we can repeat this pattern so to fill all the space available. And he had to think to a way to prove this. And he begins with the cube. He says it's obvious that 8 cubes will fill totally the space, but how can we prove it? And his idea is quite interesting, I believe. He says, I translate, consider one cube and take, the figure of course is this one, and consider and take the midpoints of all its edges, then imagine the planes perpendicular to the faces that join the midpoints. The original cube is now divided into 8 smaller cubes all around the cube. And so you can repeat this procedure for the 8 new small cubes, and again, and so you are sure that the pattern 8 cubes fill totally the space. It's a sort of, let me say, a sort of fractal reasoning. We can iterate, this procedure. And he uses the same strategy to prove, for example, that the pattern 6 octahedra and 8 tetrahedra fill the space. First step, he says that every octahedron can be divided by the bisection method, so taking the midpoints and so on, into 6 equal octahedra and 8 equal tetrahedra. And these 14 solids are placed about the center of the octahedron. So you can divide this octahedron in this way. But, second step, every tetrahedron that's smaller can be divided into another octahedron and 6 equal tetrahedra, and so on. And so he says the pattern 6 octahedra and 8 tetrahedra is divided in 44 octahedron and 80 tetrahedra, and so 344 octahedra and 672 tetrahedra, and so on and so on, and he concludes, itaque potest in infinitum procedi. And so it goes on and on and on. This is this figure that inspired also Escher. Second pattern. Third pattern, by proposition 2 of book 15, it's easy to show that one tetrahedron, we see that an octahedron can be inscribed in a tetrahedron, and so we can conclude that the tetrahedron, octahedron, and two cubes fill the space not around a point but around an edge. And this, the third result. These are the good cases, the cases that we can find the pattern that fill the space, but what about the remaining cases? And he proves that no other pattern fills the space angularity. This is an example, the example of the tetrahedron, the example of Averroes, of course. And he proves, as we have seen, that the square of AC is to the square of AE, as 4 is to 3. And so, this is the last result of book 15. He uses this idea to develop this strategy. Consider a number of equal tetrahedra which share an edge, and imagine to cut this pattern with the perpendicular plane. So to reduce the solid problem to a plane problem. The section, in fact, is composed by plane figures about a point, and the problem to solve now is the tiling of a plane by a figure that is easier and completely known. Consider one of the angles of this equilateral triangle, for example, C. The ratio between the square of the side opposite to the given angle, that's AB, and the square of one of the sides which contain the given angle is 1 to 1, whereas in the previous triangle that we have seen, the same ratio is 4 to 3, that is greater than 1. And so we can conclude, or better, Maurolico concludes, that the dihedral angle of the tetrahedron is greater than the angle of the equilateral triangle, and since 6 angles of the equilateral triangles fill a plane about a point, this means that 6 tetrahedron angles are too many, but that 5 tetrahedron angles are not enough to fill the plane, remains a gap. And so the conclusion against Averroes and Aristotle and all the commentators is that tetrahedron is not a space filler. And this is a correct mathematical proof of this, of course. And in the last part of his book, this is the manuscript, we see all the possible combination of solid, of regular solid. And for example, here we have pyramids, octahedron, congruent, it works. Pyramids, cube, and octahedron congruent, and in the remaining case is said deficient, that there's a gap, or excedunt, or better, superfluent, that means they exceed, and so he consider all the possible cases with 3 solids, 4 solids, 5 solids, and 6 solids, and he conclude that only the 3 patterns considered work. And in fact, his conclusion is the following. He says that we have to fill the space, we can consider only pattern formed by 4 cubes, 2 tetrahedron and 2 octahedron, and finally a tetrahedron, an octahedron, and 2 cubes. This is his mathematical solution to this problem of filling a space with regular polyhedra. And in the very last part of the booklet, he has the trigonometrical solution that we have seen in the previous part, that he used a pure geometrical reasoning, and in this part, we have trigonometrical consideration. He measured the dihedral angle by the table of trigonometry, and he, of course, arrived at the same conclusion. To conclude, we have other two particularities of this manuscript. We have 2 pages, or better 4 pages, where there are sort of instruction how to construct solid figure with only one sheet. And yeah, in fact, in the Implezione Loci, Maurolico mentioned the usefulness of real models of the solid. And he said these are the development of the solids. And he adds that you can construct this Platonic solid using only one sheet. And we see, this some strange thing. It says those tabs protruding from certain sides have been left to be filled with the glue. So to join the sides of the face, they are really instruction to how to construct a solid figure. And we have also this very interesting table where he puts he puts the 5 regular solids, and he puts the number of faces, the number of solid angles, that's vertices, the number of edges. And he's a mathematician. He immediately sees that there is a sort of regularity. That's the sum of the faces and solid angles is 2 more than the number of the edges. And so he concludes, observing that it's clear that in any regular solid, the number of the faces added to the number of the vertices exceeds the number of the edges by 2. Are we in front of the formula of Euler-Poincaré? Of course not. We have only a table of 5. Only 5 is not a general result. Anyway, it's interesting, in my opinion, from another point of view. In the Euclid's elements, we don't have the idea of polyhedron, a general idea of polyhedron. We have the pyramids, we have the cone, we have the sphere, we have the cube, but not the idea of what is it a general, a polyhedron. In Maurolico, we have a sort of peculiar property that he can associate to the class of some polyhedra, the class of regular polyhedra. And so a way to go toward the idea of something more general, that single figure, solid figure. And to conclude, we have seen that in this De Implezione Loci, Maurolico accepted the responsibility of Regiomontanus' heritage and shared his idea of restoration of classics. So a restoration, a mathematical restoration, rather than a philological one. The interesting novelty of his De Implezione Loci is this sort of iterating reasoning to prove the total filling of the space instead of the local filling of the space. And even more interesting is the emergence of the concept of regular polyhedron as a general object defined by peculiar properties. That's the Euler characteristics. This is interesting, in my opinion, because the emergence of a general object in mathematics is one of the peculiarity of the mathematics of the 17th century. And this is a clue that means that we are approaching this viewpoint. We have some images of the online edition of Maurolico's work. Actually, we have only 2 published volumes. because of the lacking of money. And we have only the online edition. You find it in this web address. This is a PhD doctoral PhD thesis on the implezione logic with the critical edition of this booklet. And so, that's all. Thank you.
Dizaine de minutes pour la discussion. Vous pouvez poser vos questions, je pense, en français ou en anglais. La parole est à vous.
Mais slowly, anyway.
I have a question on the first part of your talk about Euclid's edition.
You see, sorry?
A first project
Yeah.
and a second project.
Yeah.
Which means that it concerned itself for a long time with this Euclid edition. And you said that Maurolico makes standing reference to his project and his edition.
Yeah.
Do you know whether this edition were already also known to other scholars, for instance, to Cardano? Do you know how it was diffused? If it was diffused?
I believe it was only diffused, if it were, in the Jesuit schools. Yes, I believe. The second part, the compendia, maybe they were diffused. The first part is a reduction of book 5 or 7, or are, in my opinion, completely ignored by the community, because it didn't print it. It published his Index Lucubrationum, but of course it was not so diffused. And for what concerns Cardano, we know that Cardano uses Lamberti's and the Campano's edition. He didn't know at all Maurolico's work. And so probably the compendia, not only the Euclidean compendia, but also other compendia, were diffused in the Jesuit environment. Maybe it's possible, because in the Archivio of the Jesuit Society, we find some manuscript written by Clavius, but they are of Maurolico. And so maybe there were diffusions at this level.
Well, I was curious about what you said in the end, the emergence of a general notion of regular polyhedron. Of course, I'm not an expert on Euclidean traditions and editions and versions and so on. You have books 13, 14, 15,
Yeah.
and so on, but I mean, if I look at what one considers today as being of old origin, at the end of what is currently book 13, you have this proof with no theorem, right? I mean, there is, okay, so you have construction of
Yeah.
the last one, the dodecahedron, and then you have the proof, which
Yeah.
shows that any regular polyhedron has to be one of the 5 ones
Yeah.
that have been constructed. So that, to me, has always seemed as evidence that there is floating in the background there.
Yeah.
And even though there is no theorem stated,
Yeah.
and there is no formulation, there is no explicit notion of regular polyhedron, there is a proof that there are no others. So there
Yeah.
is some sort of a notion. So what? No, I mean,
Yeah. Yes. No, yeah.
This is older than Renaissance mathematics. So, so what is there more than that in Maurolico?
Yes.
I didn't see it.
Yes, in my opinion, of course, you have completely right. The last proposition of book 13 explain how to construct a regular polyhedron. But we have, as far as I know, in the Euclid, we have dodecahedron and icosahedron, and there are 5 different regular solid. In this case, one could see the idea that if you have a solid and the property of pure Euler it's true, then this is a regular polyhedron. That's a property that defines the class of a regular polyhedron. It doesn't mean if it's a tetrahedron or an octahedron, but because that property is true.
I don't understand. I mean, Euler is true for non-regular polyhedrons.
Yes, of course, but I'm talking about Maurolico. Maurolico says only that for what concern regular polyhedra, of course, he didn't do a general. No, he didn't do a general consideration. He only says that for what concern solid platonic solid, we have this relation, of course.
Well, for the 5 examples.
Exact. He didn't extend this result to every convex polyhedron. No. But he says that for all the 5 regular polyhedron, this property is true. That is a way to say, for me, it's not completely true, but from his point of view, there is a property that characterizes all these 5 polyhedron. It doesn't mean which kind of polyhedron, of regular polyhedron they are. And this is a way to determine a class of objects, not only the tetrahedron or the sphere or the cube. They're not different. They shared this property. This is a way, very, very weak, if you like, but to determine a class of object and not the singular object.
I had a question myself in connection to the procedure of tiling the space.
Mm-hmm.
I wondered, what is the concept of space in Maurolico? Because it seems like he was tiling a polyhedron.
Yeah. He uses this result, that is the result of book 15, to see, yes, if I can inscribe a polyhedron into another, we can use this result to construct a pattern for all the whole space.
But is it the terminology of space?
Locum. He used this word locum that is very, very undefined, to be honest, yes.
And my other question was in connection to the Euler characteristic and so on. The actors who developed this kind of mathematics in the 18th and 19th centuries, very often they're very much connected to the, to the mining and industry, and so of course the development of crystallography. So I wondered if there was any evidence of connection in Maurolico with, mixed mathematics in a way, because we can see the use of Arabic numbers. So other traditions than the one of classical.
No, as far as I know, there are no evidence of these connections. So he's reasoning about, in general, about solids. There are no connections with other traditions, at least for what I know.
Which kind of manuscript did Maurolico read as far as concern Averroes? Arabic manuscript?
No, he only read the program of Regiomontanus, and he says that in the title of this book that it was mentioned Averroes, but he didn't read the commentator, no.
And another question, this manuscript by Maurolico influenced the other book on Euclidean tradition in Italy, or Kepler book?
Yeah.
We have
no one mentioned Maurolico, so I can know if they, in some way, they know something about him, but there is no evidence of a direct donation, and this work was unpublished and largely unknown also, and so it's difficult to answer. We have no clues. Yes, exactly this. Maybe only some compendiums, as I've already said to Sarah, maybe were transcribed copied by Clavius, and maybe they were diffused into the Jesuit environment, but we have no notice about this, for example. We have something about the construction of a scientific instrument. Clavius has something of this, but not about Euclid.